In this tutorial, we're going to talk about differential equations. Differential equations, often written in shorthand as just DE. So a differential equation is an equation which contains derivatives of some dependent variable. They come in many forms and are an essential concept for much of maths and science. In modelling the dynamics of a system where the variables vary with time, we can form differential equations to model this variation. A common example is Newton's second law of motion. F equals ma. Force equals mass times acceleration. Acceleration can be rewritten as the first derivative of velocity, which can also be written as the second derivative of position, like so, where x is position. And this is often also written in shorthand, like so, or you may also see with two dots, like so. So this is a very common example of a differential equation. In biochemistry, cell processes such as transcription, translation, growth, etc. take time. So we can describe the variation of mRNA, protein, cell concentrations using differential equations, then attempt to solve these equations. There are a few ways we can classify differential equations in order to categorize them into different groups that share certain properties, which is what we're going to cover next, classifications. And this is so that, for example, one method of solving a differential equation may only be valid for particular classifications of differential equations. The first classification or categorization we're going to cover is ordinary versus partial. Ordinary versus partial. An ordinary differential equation, often written in short as just ODE, is an equation in which the dependent variable only depends on one independent variable. So suppose our dependent variable was x. X would only be dependent on one independent variable, say time. Therefore, any differential equations in x will be ordinary. So from our previous example, suppose force was a function of time, and then we had this side, ma, or m times the second derivative of position, would also be a function of time, and therefore x is only dependent on one independent variable, and therefore this is an ODE, an ordinary differential equation. On the contrary, a partial differential equation is an equation in which the dependent variable depends on two or more independent variables. So partial differential equation, often written as PDE. Suppose we have some variable u, some dependent variable u, that will be dependent on two independent variables. So say position and time. So an example of this might be a heated rod. So suppose we were heating a rod at one end. This side would be much hotter initially, and the heat would spread down the rod. And so at any given position, the temperature will be different, and at any given time, the temperature would be different. So a differential equation in temperature would be a partial differential equation. This is written like so. So the differential will be in terms of x or of t, in this case at least, but u will be dependent on both x and t. So the key difference will be this this del, we would call it. PDEs are a lot more complex than ODEs to solve, but it's still worth being aware of the difference between the two. Next, we're going to talk about the order of a differential equation. Order. The order of a differential equation is the highest derivative present in the equation. So we're going to do this by example. Suppose we have this differential equation, equals sin x. So here, y is our dependent variable, and its derivatives are in terms of x. So this would be an ODE. And we look at each term to determine the highest derivative present. So in this term, we have a second order derivative. In this term, a first order derivative. In this term, a 0th order derivative in effect. And this term, there is no y term, or in effect, y to the 0. This is the y to the 0th term. The highest derivative is 2, and therefore, this implies this is a second order differential equation. Next, we're going to talk about homogeneous versus inhomogeneous differential equations. Versus inhomogeneous. Homogeneous means every term in the differential equation contains the dependent variable or its derivatives, while inhomogeneous implies there is at least one term which does not. So again, by example, suppose we use the previous example again. Take a look at the previous example. Minus 3xy equals sin x. We look at each individual term and look for the dependency on y, our dependent variable. So in this term, there is y dependency, so we give that a tick. In this term, there is y dependency, give that a tick. In this term, there is y dependency, give that a tick. But in this term, there is no y term, and x is independent of y. And therefore, this is an inhomogeneous differential equation. Differential equation. On the contrary, if we had the same equation on the left-hand side, but we had it equal to 0, or perhaps y, or first derivative of y squared. These are all examples that would make this differential equation homogeneous. The fourth category we're going to cover is linearity. Linear versus non-linear. Linear implies every term is of the form coefficient times derivative, such that the dependent variable and its derivatives are never in any function or to any power, or multiplied by themselves even, by each other I should say. So that's to say, every term of the form function, some function, multiplied by some derivative. So this is the general form to say the nth derivative of our dependent variable y. And this function, so long as there is no y dependency, this term would be linear. Now for a differential equation to be linear, every term must be of this form. Every term must be linear. Let's take a look at the previous example once again to consider whether it is linear or non-linear. Minus 3xy equals sin x. So we look at each term and determine if each term is linear. And if every term is linear, then the entire differential equation is a linear differential equation. So in the first term, we have a coefficient of 1 in effect, and a y derivative, not in any function, so this term is linear. Here we have x as the coefficient. X is not dependent on y, so our function is just x, and it has no dependency on y. Then we have our y derivative, so yes, this is linear. Here our coefficient is minus 3x. Again, x does not have any dependency on y. And then we have our y derivative, of course it's y or one of y's derivatives. So yes, this is linear. And this is effectively the y0th term. Sin x is not dependent on y, and therefore it has a linear form. This term is linear. Every term is linear, so this is a linear differential equation. Examples of terms that would be non-linear would be something like y times the first derivative of y, or y squared, or some function of y, so sine y. These would all be non-linear terms. And if any of these were present in the differential equation, then the differential equation would be non-linear. The fifth and final category we're going to consider is coupled, whether a set of differential equations are coupled or not. So this doesn't necessarily apply to just one differential equation. This is when you have multiple differential equations. So coupled implies there are two or more differential equations, as I said, in which they share two or more dependent variables. And then in this way, the variation of the dependent variable of one differential equation is dependent also on the variation of the dependent variable of another differential equation. That was a lot to take in, so I'll give an example. Suppose we had two variables, x and y. dy by dx equals, dy by dt equals x squared plus 10, for example. And we also had another differential equation, dx by dt equals sine y. So we can see the y term here is determined by the variation of this differential equation, the solution of this differential equation, but also the x term here is determined by the solution of this differential equation. And therefore, in this way, their variation is dependent on one another, and therefore they are said to be coupled. A lot of the time, differential equations can't be solved analytically. This is because integration is sometimes impossible for more complex equations, such as, in general, the Hill equation. However, they can be solved numerically using computational methods. Numerical methods. There are many different types of methods for different situations, but the hard work is usually done for you in special modules of programs such as MATLAB or SciPy in Python, or NumPy in Python also. So you wouldn't have to hard code anything. So a few examples include the Euler method. We call this a first order iterative method. While very easy to code by hand, it is highly inefficient and highly inaccurate. So I wouldn't recommend using the Euler method, apart from just to practice programming. The second method is second example, is the trapezium rule, or the Simpson rule. Now these can be done by hand, but if you have access to computers, certainly would recommend doing a computational method such as, final example, runge cutter. Now this iterative method is much more efficient than the first two, much more accurate than the first two, and it's a up to a 12th order iterative method, and in this way it is far more accurate. And as I mentioned, the difficult part of coding for this methodology is already done for you in programs such as MATLAB and Python, so I would recommend using methods such as the runge cutter. That concludes this tutorial. To reiterate, differential equations are an essential concept for much of maths and science, and especially for modelling in biochemistry, in cell biology, and in synthetic biology. And therefore, being aware of differential equations, their categorizations, and how to solve them is very essential.